So what's the real difference between the deep boom of a drum and the super sharp whistle of a flute? Well, it all comes down to the basic characteristics of sound waves, and today we're going to break them down piece by piece. All right, so we know sound is a wave, right? It's just a disturbance moving through the air. But that brings up a really big question. If it's a wave, how in the world do we measure it? I mean, what kind of tools do we even have to describe a sound wave scientifically? Well, that's exactly our mission today. We're going to build a complete toolkit for measuring sound. Okay, first up in our toolkit is something called wavelength. This one is all about measuring the physical distance of a single wave. You can almost think of it as the wave's footprint as it moves through the air. Now, let's look at the official definition. As a sound wave travels, it creates these two alternating zones. You get areas where the air particles are all squished together. We call those compressions. And then you get areas where they're all spread apart, and we call those rarefactions. So the wavelength is just the physical distance from the start of one compression to the start of the next one. It's a real physical length, something you could literally measure with a ruler if you could see it. In physics, we have a shorthand for this, of course. We use the Greek symbol lambda. And since it's a measure of length, its standard SI unit is, you guessed it, the meter. Makes perfect sense, right? Okay, so we've got the wave's length down, but that doesn't tell us how powerful the wave is, does it? For that, we need our second tool, and it's called amplitude. This one is all about measuring the wave's intensity, or its energy. Now, here's a super important point to get. The particles in the air don't actually travel all the way from, say, a speaker to your ear. Nope, they just oscillate or, wiggle back and forth around their normal resting position. Amplitude is simply how far they wiggle from that resting spot. So a bigger wiggle means a more intense disturbance, a more powerful wave. And what's really cool is that the units we use for amplitude can actually change depending on what the sound is traveling through. So in air, we usually talk about the change in pressure, and we measure that in pascals. But if the sound wave is moving through a solid, like a wall, we'd measure the actual physical displacement of the particles, and that would be in meters. The main idea is the same, how big is the disturbance, but the units just adapt to the situation. All right, let's do a quick toolkit check. We've got distance covered with wavelength, we've got intensity covered with amplitude, so what's missing? Time. Now let's bring time into the picture. And for this, we actually have two concepts that are basically two sides of the very same coin, time period and frequency. Time period is, well, pretty much exactly what it sounds like. It's just the amount of time it takes for one full wave cycle. That's one compression and one rarefaction to pass by a certain point. So, to put it simply, how long does one complete wiggle take? That's your time period. We use a capital T to represent it, and since it's a measure of time, its SI unit is, of course, the second. Okay, now for its partner, frequency. Think of it this way. If time period asks, how long does one wave take to pass, frequency asks, how many waves pass in 1 second. See the difference? It's all about how often or how frequently those wave cycles are happening. The symbol we use for frequency is the Greek letter nu. It kind of looks like a curvy V, and its unit is the Hertz, or Hc for short. It's named after the amazing physicist Heinrich Hertz. And it's simple. 1 Hertz just means 1 cycle, or 1 oscillation per second. When you put them side by side like this, their relationship becomes super clear. They're total opposites. They're inverses of each other. Think about it. A long time period means a low frequency. The wiggles are slow and lazy. But a really short time period means a high frequency. The wiggles are happening super fast and are all bunched together. And the math that connects them, it's actually beautifully simple. Let's just walk through it logically. So if frequency, that's nu, is the number of waves that happen in 1 second, then how long would just one of those waves take? Well, it would have to be 1 second divided by the total number of waves, right? So 1 divided by nu. And hey, wait a second. The time for one wave, that's our definition of time period, t. So boom, there's our formula. T equals 1 over nu. And of course, that means nu also equals 1 over t. All right, let's put that formula to the test right away with a quick example. If a sound wave has a frequency of 500 Hertz, what's its time period? Let's figure it out. This is super straightforward. We just use our formula. Time period equals 1 divided by the frequency. So that's 1 divided by 500, which gives us 0.002 seconds. I mean, just think about that for a moment. That means each full wave cycle is over and done within just 0.002 of a second.
That is incredibly fast. Okay, so now we have our full toolkit: wavelength, amplitude, time period, and frequency. But so what? Why does any of this actually matter? Well, this is where it all comes together, because these physical properties are what create everything we actually hear.
And this slide right here is probably the most important takeaway of this whole explainer. It's super simple. Amplitude determines the loudness of a sound. A bigger amplitude means a louder sound. Easy. Frequency, on the other hand, determines the pitch. A sound with a higher frequency has a higher pitch. Think of a little bird chirping. And a sound with a lower frequency has a lower pitch, like a deep bass drum.
Okay, quick pop quiz for you, just to make sure you're with me. If a sound source has a frequency of 10 Hertz, how many times does it vibrate in 1 full minute? Go on, take a second to think. All right, got it? Remember, 10 Hertz means 10 vibrations every second. And we know there are 60 seconds in a minute, so you just do 10 times 60, which gives us 600 vibrations. See? Simple when you break it down.
So let's do a super fast recap of our entire toolkit. We've got wavelength, that's the length of the wave in meters. We've got amplitude, that's the intensity, which we hear as loudness. Then there's time period, the time it takes for one wave to pass. And finally, frequency, how often a wave passes per second, which we hear as pitch. And that all boils down to our final golden rule. Honestly, if you remember just one thing from all of this, let it be this. Higher frequency means higher pitch. Higher amplitude means louder sound. Once you truly get that simple connection, you've unlocked the secret to how the physics of waves creates the rich world of sound that we experience every single day.